logistical thing. I realize that it's a very long class and it's also in the evening. It's fine for people who feel as if they are falling asleep to sort of get up, go wash their face, etc. As long as you don't disturb the class. Okay. If you actually fall asleep, I have the roster of people's faces, and I remember your face, and then things won't be good. Okay. So please don't do that. I realize that if I'm on the other side, as beautiful as my voice is, that sometimes it can be so thick, and then you may fall asleep. So it's okay if you need to get up and stretch, etc. If all of you get up at the same time, it will be really difficult, but it's completely fine. Moving around is okay as long as you're not disturbing. Going and washing your face and coming back is completely okay, but just please don't sleep. Okay. Okay. So this is the slide that I was actually doing without showing the slide. Essentially this weight and switch graph was the motivation, but really what we want to do is to improve the performance of uniform cost search, which by making it take into account not just cost till now, which is G value, but also cost to go, which is the H star value. But cost to go is not easily available. So I look for approximations of cost to go. I'll do this in two phases. First, I want to make you understand that if I were to get an approximation that is a probable lower bound, that means it's never going to be greater than H star of n for even single node. Remember, this is an approximation for every search node. Okay, each search node has a separate H star value. Okay, and for every search node you need to give an approximation H of n that's such that for all n, H of n is less than or equal to H star of n. This would be called lower bound heuristic. Okay, I'll basically first try to argue for you that lower bound heuristics have the property that we would want, which is that if they are lower bound everywhere, and if you just do search with them with G plus H as the priority function rather than just the G or H. Okay, in fact, you never used H before. Okay, so if you just use G plus H as the priority function, that would be F value would be G plus H value, and then you pick the lowest F value nodes and expand them further until you find the goal node and you stop them. Then you are guaranteed to find optimal goals this way. That means when you stop, the goal that you stop with is an optimal path to the goal. And it turns out that the reasoning for this is almost the same as the reasoning for why uniform cost search was optimal. Remember, the basic idea would be there is this partial path and you stopped with this node. Could the partial path, which currently is equal to this, could it have become smaller in cost? And we argued it can't become smaller in cost because it just have epsilon positive cost. Now, however, what's interesting is you're comparing not the G values but the F values. The F is the cost to go to that node, a cost to reach that node plus approximation of the cost to go from that node. But the approximation is a lower bound. So whatever is the true cost through that node will be higher than whatever you found as the F value right now. If my current node is already a goal node with value 10, and this path, partial path has value 10, it can only be more than 10, can't be less than 10 because this cost to go part is a lower bound. So it will either be equal, in which case I just have two goals of equal type, or it will be higher, in which case it will actually be a costlier path. But I have found a bird with full, I found a node with full path. So that can be worse than the other one. That's the proof. Okay? So, So, just for a second. So basically I'm going to prioritize by bounding the H star by taking H to be a bound on H star. If the H is a lower bound, so I can either consider H1, which is always a lower bound, or H2, which is a higher bound, upper bound. Now it turns out that lower bounds have this property, optimality property. Upper bounds have an interesting property. They will get done faster, but no optimality. Okay, so if I actually wind up having two lower bounds, H1 and H2, such that H1 is less than or equal to H2 is less than or equal to H star, then which one would you pick? H2, right? Because you already know that the higher your estimate of cost to go, the better the search. But if your estimate is more than the true value, guarantee of optimality is gone. So if I have two lower bounds, one of which is a better, which is higher than the other lower bound, that means it's closer to H star, then I pick that one. This leads to the notion of informedness of heuristic. A heuristic is admissible if it is considered, if it is a lower bound on H star. One heuristic is more informed than another heuristic if both are admissible, and first heuristic is always equal to or greater than the second heuristic at every point. Right? Because it's now closer to H star. Okay? So that's the notion. So basically you want the lower bounds and you want a tighter lower bound. Tighter lower bound means it's come as close to H star as possible. Coming equal to H star is great, but that will involve computing the heuristic where you'll spend all your time. Okay? If you understand this, essentially now if you start doing the search to be G plus H, okay, then you get, I mean, if there was a huge orchestra here, right now it will spring to life and have a crescendo because this is A star. That's it. Okay? So A star is nothing but doing search with evaluation function f, which is equal to G plus H, where H is a lower bound on H star. Within that argument opens up a whole entire can of worms, such as, where do you find these lower bounds? You know one way, you put H equal to 0, that's a lower bound, you guarantee it to be optimal. Okay, that's what uniform cost search does. The question is, can you find non-trivial lower bounds that are closer to H star? Okay, and we will see this notion of problem abstraction. We'll understand this notion of problem abstraction. If you abstract the constraints away from the problem and solve this abstracted problem exactly, the solution to the abstract problem winds up being a lower bound on the real problem. Whatever I said looks like gobbledygook, especially in the evening. Abstraction involves removing constraints. So imagine I'm trying to find a path to that guy out there. Right now, the shortest path, I have to kind of figure out what's the best way to reach that guy. I will abstract. I'll abstract and say, I'll close my eyes and assume that all the chairs have disappeared. All of you also have disappeared. Only that guy is present. Now can I find the optimal path to that guy? Yeah. That's just the straight line distance. I take his coordinate, my coordinate, take the Euclidean distance, that's the optimal path. Now, Euclidean distance is guaranteed to be a lower bound on any real distance. Because now I start putting chairs, the chairs can only make the cost higher. Unless you start putting wormholes in the space between me and him, which will start reducing the Euclidean distance between me and him. Okay? Mostly putting constraints on the space makes the distance longer or leaves it undisturbed. So that's just an example of actually finding a low bound heuristic. Straight line distance, I got the straight line distance by acting as if everybody disappeared. Okay? In Manhattan, basically if you're trying to figure out what's the distance between 2 points in Manhattan, you could still do straight line distance. That would be a lower bound. But you could also realize that Manhattan has Manhattan distance. How many of you have been to Manhattan? Okay, as far as this course is concerned, the only interesting thing about Manhattan is the fact that it has a grid-shaped roads. Okay, so to go from a point A to point B, you have to go like that. You can't go like this. can't go like this. Anybody actually went to Manhattan? You can go like this because of one sad road there, Broadway. Okay, Broadway makes this argument go away because Broadway is actually non-grid, it cuts through grid. But imagine Broadway doesn't exist. Okay, then Manhattan is just a grid of roads. And the distance in Manhattan between 2 points, so if Manhattan is like a plane, then this is x1, y1, this is x2, y2, then the optimal distance is x1 minus x2 squared plus y1 minus y2 squared. That's the Euclidean distance, and that would be the lower bound. But because I know that in Manhattan most of the time I can't go like that, I have to go like this, right? Or I have to go like that. That's called Manhattan distance. In fact, Manhattan's real claim to fame is it was the origin for the name Manhattan distance, as far as you are concerned in this course. And what's the Manhattan distance? It is x1 minus x2 modulus plus y1 minus y2 modulus. Those of you who are way ahead of me might know that this is called L2 norm in distances, and this is called L1 norm in distances. Okay, but we'll talk about that later. But essentially, Manhattan distance is, if you are in Manhattan and you are using straight line distance as the approximation of the distance to go, would you be optimal? Would you be optimal? If you are in Manhattan and you are using straight line distance to go as the approximation heuristic, would you be optimal? Yes, because it will be a lower bound. The true distance cannot be better than the straight line distance. But if you are in Manhattan and you realize that nobody gets to go in straight line between 2 points unless you are a crow, even crows keep hitting into the Empire State Building. So you do realize that you have to go in the zigzag pattern. And so there the distance is actually x1 minus x2 plus y1 minus y2 modulus. That actually is larger than the straight line distance. Both of them are better, both of them are lower than the true distance. Because in Manhattan at some point of time there may be some roads which are one way, some roads which are closed, and so are some roads which have a huge traffic jam. So the actual distance might be much higher than either of these. So suddenly you have a situation where h Euclidean of n is less than or equal to h Manhattan of n, which is less than or equal to h star of n. You don't know what h star is, but you know that these will be lower bounds. And you also know one lower bound is better than the other lower bound. So I gave you two heuristics. One is actually more informed than the other. Okay, more to the point. In fact, let me go to. I'll come back to this in a minute, but let me go to this because this is the 8 puzzle problem. Okay, so in the 8 puzzle problem, I can decide if I have this as the start state, this as the goal state. I need to sort of decide the distance to go is how many moves does the blank have to make before you can convert this state to this state. Right? The exact cost to do that, you will actually have to do the real search, full search. That will be too costly. So then I need to abstract this problem. One abstraction is assume that the blank can travel any which way, anywhere it wants by Euclidean distance. Okay, actually no, in fact no. What I'll do is, I'll assume that blank can travel anywhere it goes by just one jump. Okay? In that case, then all I need to know is how many tiles are in the wrong position. How many non-blank tiles are in the wrong position. If I count the number of tiles in the wrong position, that number is guaranteed to be lower than the total number of moves blank has to make. Remember, I only count the number of non-blank tiles that are in the wrong position. It's very important. If you do that, then that sum would be lower than the total number of moves blank has to make. And that's called the misplaced tiles heuristic. Okay, misplaced tiles heuristic, you are saying you can just teleport yourself to wherever you want. You could have done that in Manhattan distance too. In fact, suppose you could just say, I have the ability to teleport wherever I want. I don't even need to use Euclidean distance. I'll just, in 1 unit time, I'll just go to wherever I want. That would be even more of a lower bound. But then teleportation would be actually kind of illegal in Manhattan, and so that would be, even though it's lower bound, it's actually less than the Euclidean distance, which is less than the Manhattan distance, which is less than the true distance. So you have 3 heuristics now, each of which is more informed than the other. So in the case of misplaced tile distances, if I use teleportation, then I would just count the number of misplaced tiles. Okay? And that would be a lower bound. You had a question?
I answered it.
Good. Okay. The other point is, well, instead of teleportation, that means I have made the problem so simple that I can just teleport myself. Essentially, the thing that's interesting about this is if you can lift the tiles and put it in the right place, obviously the number of moves is very small because you just have to put the misplaced tiles in the right position. That just makes all the constraints go away. The thing that is hard is you can't actually move things to arbitrary places. The next thing I'll do is, instead of just counting the number of misplaced tiles, I'll count for each misplaced tile how far it is from its intended position in the goal state. You understand what I'm saying? How far it is from its intended position from the goal state. The distance now, rather than use Euclidean distance, this is meant for Manhattan because it's grids, columns and rows. So I count for each tile, let's say tile 7, it's in this position here, it is supposed to be in the position here. So its distance from its true position is 0. How about 6? It's in this position here, and it is in this position here. Its distance from the true place is 2. Similarly, 5, it's here, it has to be here. The distance would be 1, 2, 3, 4. If I add all those for each tile, each of the non-blank tiles, their distance from their true position, this you can do. This is just basically just counting x1 minus x2 plus y1 minus y2 modulus. This doesn't require you to solve the problem in any real sense. Right? Okay? If you add those numbers up, then so it turns out that between this start state and this goal state, if you count misplaced tile heuristic, the heuristic value is 7. And if you count the Manhattan distance of the misplaced tiles and sum them up, the heuristic value is 18. Both of them are lower than the true cost. Which would you rather use? 18. So in fact, if you are doing search algorithms on Manhattan and the 8 puzzle problem, you can see how big a difference is made when you use this heuristic instead of this heuristic. Both are lower bounds, but one is closer to its start. So when you are abstracting the problem, abstract it just so much that you can solve the remaining problem in reasonable amount of time. This reminds me of Einstein's saying that everything should be made as simple as possible but no simpler. So you should abstract it as much as possible but no more. Funny, like warm and fuzzy kind of a sentence. And in fact, it turns out that I'll show you some discussion showing that the field as a whole did not know what are good heuristics for the longest time. The general assumption is a heuristic is something that should be computable in extremely low order polynomial time. Okay? And actually, since I'm talking about that, let me show you that picture. Yeah. Oh, no, wait, we'll come back to this. It's a beautiful picture, but we'll come back to this in a minute. But I will go to, I'm shifting back and forth, but wait a minute. Okay, wait one second. So what I am trying to show you, yeah, this one. Yeah, it was just on the other side. Sorry. Okay. By the way, this is the most important picture in life. Okay. What's the meaning of life?
42.
42. What's the meaning of this course? This. Okay. In general, many a time you'll find that this sort of trade-offs exist under very different guises. By the way, people who didn't understand what's the meaning of life being 42, you're in the wrong class. You have to figure out why it is 42. Okay. Okay. So this picture is showing a very important truism that people don't realize about what is happening for A-star search. You find, so in this picture I'm talking about different heuristics, all of which are admissible on the x-axis. And the total amount of time you spend computing those heuristics during the search. Remember, since I'm only talking about all heuristics that are admissible, optimality is a given. When I'm done, optimal solution is a given. The real question is, of all the optimal searches, which one is going to be more efficient? The question then is, which of these heuristics should I be picking? Right? Of course, these heuristics obviously are abstract, but the point is, imagine the total amount of, these are the cheap heuristics. This is like h equal to 0. Every node, I'll assume the heuristic cost is 0. That one would spend the least amount of time in the heuristic computation phase. The other extreme is all nodes I will compute h star as the heuristic value. I'll do it. I'll actually do the real search for each node and compute h star. Just so that I can tell my friends, look, I do least amount of search afterwards. In that case, the total amount of time I spend in computing the heuristic is that much. So in general, as the informedness of the heuristics increases, the total time you spend computing the heuristic increases. At the same time, the total time you spend computing the expansions during the search reduces. Because with h star, you do the least amount of expansions. You just go directly on the optimal path. Right? You go just directly on the optimal path. And so you will wind up spending the least amount of node expansions. But then that was because you spent all your time beforehand figuring out what is the true cost to go from each node. Okay, so what is the best heuristic? Well, the best heuristic should be the one that optimizes the total cost spent in computing the heuristic plus doing search with it. So if you add these two curves, the blue curve comes, approximately. And that what that blue curve says essentially is you expect the search to be the most efficient, not at the cheapest heuristics, not at the most accurate heuristics, but somewhere in the middle. You understand that? Okay? This is the minimum. You need to understand that you do expect to have to spend a certain amount of time in computing the heuristic before you do well on the overall search, right? Because if you spend too little time computing the heuristics, you're going to spend too much time computing the expansions. If you spend too much time computing the heuristic, if you spend too much time computing the heuristic, you'll spend very little time doing the expansions, but then you lost all the time there. The time comes from the same bucket. The $1 billion or $64 billion question is, where do these lines cross? Okay? It's very much problem dependent. But as a field, people used to think that a heuristic is something that will take 2 lines of code to write. Okay? So if you see any early textbooks on AI, they will mostly talk about heuristics of the type of straight line distance or maybe Manhattan distance. That is it. That means we basically assumed that these curves would be such that the minimum will appear there. It actually so happens that for most problems, most real problems, you might have to spend quite a high amount of time in the heuristic computation, and you will still do well in the total time. You understand what I'm saying? So if you are comparing yourself to your friend, and your friend is spending less and less time on the heuristics, that doesn't necessarily mean you are going to be losing. Right? Because you might be doing less time in the search. You're spending more time on the heuristic, you might wind up spending less time in the search. Okay, the real question is, where do you expect this crossover occurs? Generally, the sort of unsaid conventional wisdom was that low polynomial cost heuristics are the only ones that will win. In science in general, unsaid biases are the ones that keep you behind. So if you ever find an unsaid, an unarticulated bias, try to break it and see what happens. Okay? As a field, people started taking costly heuristics which are in this direction, started even looking at it only like 15 years back. And then they found that actually they do much better. In fact, there is an idea for puzzle problems called pattern databases. A pattern database, instead of computing either the misplaced tiles or the Manhattan distance to the misplaced tiles, it goes about in a different way. It says, let me take a pattern of the goal, a sub-pattern. This is the entire goal state is the full goal state. Suppose I just consider this pattern. So I would say I'm only interested in taking this state to a state where 3, 4, 5, 6, 7 are in those positions. And to make my life simple, I'll assume all other tiles, their faces have been whited out. I don't care where they are. Admit to yourself, realize to yourself that the problem I'm talking about is cheaper than the full problem. Because I'm only getting part of the solution, not the full solution. But it's also significantly more complex than either misplaced tile heuristic or the Manhattan distance heuristic. Because you actually have to write an algorithm, a real search algorithm, which goes from a configuration which basically has 3, 4, 5, 6, 7 in these places, and the 1 and 8 have been whited out. And it needs to get into this position. It's a cheaper search problem. It is an abstraction of the original problem, but it's quite costly still. People didn't even check these kinds of things as heuristics before. Because why? It looks like that those would be the bad kind of heuristics because they would be somewhere here. The best heuristics for tile puzzles turn out to be pattern database heuristics. And for those problems, you spend a humongous amount of time. You spend a humongous amount of time computing the heuristic, and yet the problem itself is such that the minimum kind of occurs here. And you would have found it only because you checked. Do you understand what I'm saying? Okay, so the heuristics, if you can remember one sentence summary of what I just said, heuristics can themselves be a pretty darn costly search problem. They don't have to be a two-line solution. And in fact, one of the nice things is, if I remember correctly, one of your last questions of the project will force you to consider heuristics that actually involve spending a lot of time. And yet, total amount of expansions will be reduced by doing it. There was a question. Yes?
Could you recursively apply that heuristic with whiting out the tiles? So white out one tile and apply that heuristic with white out one tile?
So there are variations of that. The biggest interesting questions of those winds up being whether you can still be admissible. So I can send you a link to a paper on pattern database heuristics, which will basically talk about this notion of union pattern databases, where you consider one heuristic from one pattern, another heuristic from another pattern, and if you can add them up, that will be just great. But sometimes when you add them up, you might cross H star. And if you cross H star even once, you are no longer up. Okay? But the bigger point is that heuristic computation can actually be quite an involved process. And in general, think of one man's abstraction is another man's real problem. One woman's abstraction is one other woman's real problem. Okay? And it doesn't have to be the case that heuristics are just abstractions. An abstraction can be just pretty costly still. Okay? Yeah, so by the way, this is a very important thing. It was not understood generally for quite a long time, and this understanding helps you in multiple places. Okay, because it's the overall time you spend that matters, not how you spend which. And this is exactly why, by the way, I would argue that my favorite example for this is, actually, I mean, it's this is kind of connected to a lot of other things like exploration, exploitation, and also things like, in a qualitative way, how much time you should spend looking at the entire exam before you start answering any single question. I mean, if you see a friend of yours who's just basically looking at the entire exam, hasn't started writing even a single sentence, it's not guaranteed that you would do better than them. Okay, they may have thought up the entire solution in their head and they just wrote the answers down at the beginning. So that's heuristic time spent versus the search time. Okay, there was another question. But that's an abstraction, that's sort of an metaphor. But the bigger technical point here is you do have to consider heuristics. That can take exponential time. Because the only thing that matters is whether the total search time is reduced. And in many cases, actually, the total search time is reduced by considering some low exponential heuristics. And it's quite counterintuitive for most people because they think heuristic should be, the problem with heuristic is this idea that it would be considered a rule of thumb. And rules of thumb are supposed to be easy to compute. Rule of thumb is a bad analogy for heuristics. You can't compute pattern database heuristics as a rule of thumb. Okay? There was another question. Yes?
So from how you were describing this wisdom about the necessity of heuristics, it seems, or at least I got the impression, I don't know if you can tell me if this is correct or not, that there is no way of knowing whether a heuristic will be good or whether it will say.
No, they will all be good. The question is which would be the best heuristic. They will all be good. They'll all be optimal.
Okay, but how do you know if it won't go beyond, if it won't end up taking you more time than the optimal?
No. That's a very interesting question, but I hope that's the last time you ask that question. In the best sense possible, okay? There are two very different points. One is